My name is Jonathan Mukisa, and I am originally from Uganda. I was recently admitted to the PhD program in IT Convergence Engineering at Kumo National Institute of Technology here in South Korea. My research interests lie at the intersection of distributed systems, artificial intelligence, and digital healthcare infrastructures. Today's healthcare systems are becoming increasingly digital, distributed, and data-driven. Patients now interact with many different technologies, including mobile applications, wearable devices, telehealth platforms, and hospital information systems. Together, these technologies form a large and complex network of data sources and decision-making systems that influence healthcare delivery. However, despite these technological advancements, many healthcare systems still operate in fragmented and reactive ways. Different platforms often function independently without coordinated intelligence. Many systems struggle to operate effectively in environments with limited or unstable connectivity, and there are often limited mechanisms for transparency and accountability when AI-driven decisions are made. My research seeks to address these challenges by investigating how intelligent digital systems can operate reliably, responsibly, and collaboratively within such complex, ubiquitous environments. The central vision of this work is a concept I call verified autonomy in ubiquitous networks. This framework explores how distributed intelligent systems can combine adaptive intelligence, operational resilience, and transparent accountability in large-scale digital ecosystems. Instead of viewing intelligent systems as isolated algorithms, this research treats them as components of a broader environment where humans, machines, sensors, and services continuously interact. To explore these ideas in practice, I propose the development of Life+Care, a digital healthcare sandbox platform. Life+Care will enable coordinated interactions among patients, doctors, caregivers, hospitals, and intelligent services. At the same time, it will serve as a research testbed where key concepts such as adaptive intelligence orchestration, offline resilient operation, and post-hoc accountability can be implemented, studied, and evaluated in realistic healthcare scenarios. Through this platform, the research aims to better understand how future healthcare systems can be designed to be intelligent, trustworthy, resilient, and human-centered. My academic and research journey has focused on the design of intelligent distributed systems that operate across multiple devices and environments. During my undergraduate and graduate studies, I have worked with several technologies that contribute to this vision, including federated learning, deep learning, blockchain architectures, and large language models. These technologies each address different challenges in modern digital systems, particularly those involving large-scale distributed data and intelligent decision-making. For example, federated learning enables machine learning models to be trained collaboratively across decentralized devices without requiring raw data to be shared. This approach is particularly relevant in sensitive domains such as healthcare, where privacy and data protection are essential. I have also explored blockchain-based systems that support decentralized trust, transparent logging, and verifiable transactions across distributed participants. In addition, my work has included research on distributed routing systems and AI-based architectures that coordinate activity across multiple nodes in a network. These experiences gradually led me to a central question: rather than studying these technologies separately, how can they be integrated into a unified architecture? This question forms the foundation of my proposed research on verified autonomy for intelligent healthcare ecosystems. When we look at modern healthcare systems today, we see incredible advances in technology, but we also see a lot of fragmentation. Patients often interact with many separate systems: one application for appointments, another for wellness tracking, another for telehealth consultations, and yet another for accessing medical records. These systems rarely communicate smoothly with one another, which can lead to gaps in care coordination. Another challenge is that many digital health solutions depend heavily on stable internet connectivity. In reality, connectivity can be unreliable, especially in rural areas, developing regions, or emergency situations. Systems that completely depend on continuous connectivity can therefore become fragile. At the same time, Artificial intelligence is increasingly being introduced into healthcare decision-making. While AI can be extremely helpful, it also raises important questions about transparency and accountability. If an AI system suggests a medical action or recommendation, we need mechanisms to understand how that decision was made and whether it can be trusted. These challenges motivate the core question of my research: how can intelligent distributed systems operate autonomously while remaining resilient, transparent, and accountable? The main objective of this research is to design and evaluate a framework that I call Verified Autonomy in Ubiquitous Networks. The idea is to build intelligent systems that can operate autonomously while still remaining transparent, verifiable, and trustworthy. To achieve this, the research focuses on three major areas. The first is adaptive intelligence orchestration, which means designing intelligent agents that can coordinate their actions dynamically depending on the context of the system. Rather than isolated algorithms, the system becomes an ecosystem of cooperating intelligent components. The second objective is offline resilient operation. Real-world systems must continue functioning even when network connectivity is disrupted. This requires mechanisms such as local data storage, delayed synchronization, and edge-based processing. The third objective is post-hoc accountability, meaning that system decisions can always be traced and verified afterward. By combining secure logging, traceability mechanisms, and decentralized verification techniques, the system can remain trustworthy even when autonomous components are involved. Together, these objectives form the foundation of the Life+Care research platform. To study these ideas in a practical environment, I propose the Life+Care platform, which will serve both as a functional healthcare application and as a research sandbox. Life+Care is designed as a patient-centered digital ecosystem. In this environment, multiple participants interact with the system, including patients, doctors, caregivers, hospitals, and administrators. Each of these participants plays a different role, and the platform coordinates interactions between them. The system includes modules for appointment scheduling, care plan management, wellness monitoring, telehealth communication, secure messaging, and clinical documentation. These features simulate many of the workflows that exist in real healthcare environments. From a technical perspective, Life+Care will be built using a modern architecture that includes a React-based web interface, a Flutter mobile application, and a Django REST backend connected to a PostgreSQL database. By embedding research experiments into this platform, the project can evaluate new ideas in a realistic setting rather than only through theoretical models. One of the central ideas in this research is adaptive intelligence orchestration. In traditional systems, components often operate independently. However, in complex environments such as healthcare ecosystems, intelligent components must collaborate and coordinate their actions. Within the Life+Care system, intelligent agents may analyze patient wellness data, symptom reports, or behavioral patterns. When certain patterns are detected, the system can coordinate actions across multiple stakeholders. For example, if a patient reports symptoms that suggest a potential health concern, the system could automatically recommend a telehealth consultation, notify a caregiver, or update elements of the patient's care plan. Large language models may also play a role in enabling natural communication between patients and the system. Patients could ask questions about their health data, receive explanations about care plans, or get guidance on everyday health management. The goal is not to replace healthcare professionals but to support them by improving coordination and awareness across the system. Another important aspect of this research is ensuring that systems remain functional even when connectivity is disrupted. In real-world environments, especially outside major urban areas, stable internet connectivity cannot always be guaranteed. Healthcare services must therefore be designed to operate under intermittent connectivity conditions. In the Life+Care platform, devices will be able to store health information locally when the network is unavailable. For example, a patient's mobile device could record wellness check-ins or symptom reports while offline. Once connectivity is restored, the system will synchronize this information with the broader platform. Edge computing mechanisms can also allow certain analyses to occur locally on the device rather than relying entirely on centralized servers. By incorporating these capabilities, the system becomes more resilient and capable of supporting healthcare services in a wide range of environments. As systems become more autonomous, accountability becomes increasingly important. In healthcare environments, decisions and recommendations can directly affect patient outcomes. Therefore, it is critical that system actions remain transparent and traceable. The Life+Care platform will include mechanisms for post-hoc accountability, meaning that every important action taken by the system can later be reconstructed and verified. This will be achieved through detailed logging systems, audit trails, and potentially blockchain-inspired verification mechanisms that create tamper-resistant records of important events. For example, when an AI assistant generates a recommendation or modifies a care plan, the system will record the context, the reasoning process, and the resulting action. These records allow clinicians, administrators, and auditors to understand how the system behaved and whether those actions were appropriate. Healthcare data is extremely sensitive, which makes centralized data collection challenging. Federated Learning provides an alternative approach where machine learning models are trained collaboratively across distributed devices or institutions without sharing raw data. In the Life+Care ecosystem, Federated Learning could allow hospitals, clinics, or patient devices to contribute to shared predictive models while keeping their underlying data private. Each participating node trains a local model using its own data. Instead of sending raw data to a central server, the system shares only aggregated model updates. This approach preserves privacy while still enabling collective learning across many participants. By integrating Federated Learning with the broader Verified Autonomy framework, the research explores how collaborative intelligence can emerge while maintaining privacy and accountability. The Life+Care platform will use a modern multi-tier system architecture. The presentation layer consists of two main interfaces: a React-based web application and a Flutter-based mobile application. These interfaces allow patients, doctors, and administrators to interact with the platform in ways that suit their needs. Behind the user interface is a backend built using Django REST framework. This backend exposes structured APIs that support authentication, messaging, telehealth coordination, care management, and system monitoring. The system's data layer will be implemented using PostgreSQL, which stores information such as user profiles, health records, communication logs, and system events. The architecture will also support containerized deployment, making it easier to scale and manage across different environments. This research aims to make several contributions to the field of intelligent distributed systems. First, it introduces the concept of verified autonomy in ubiquitous networks, which integrates adaptive intelligence, system resilience, and accountability into a unified framework. Second, it demonstrates how these concepts can be implemented within a practical system through the Life+Care platform. This bridges the gap between conceptual research and real-world applications. Third, the research explores how technologies such as federated learning, blockchain-inspired verification, and AI-assisted interaction can be orchestrated within complex ecosystems. Ultimately, these contributions aim to advance the design of trustworthy intelligent infrastructures capable of operating in real-world environments. Looking forward, the broader vision of this research is to understand how intelligent systems can support trustworthy digital ecosystems. While the Life+Care platform focuses specifically on healthcare, the architectural principles developed in this research could apply to many other domains where distributed intelligence is required. Examples include smart cities, autonomous transportation networks, industrial IoT systems, and collaborative digital services. By demonstrating how verified autonomy can be implemented in practice, the research hopes to provide guidance for designing systems that combine autonomy with transparency, resilience, and accountability. Ultimately, the goal is to ensure that technology serves people in ways that are responsible, trustworthy, and beneficial for society.